You can go a little bit after the
Hey everybody, Molly Lopez, Managing Director for LEAP, and very happy to introduce Marcus. Marcus's talk today. Marcus is an associate research scientist and has worked at CCSR since 2013. His expertise is in using Bayesian inference methods to estimate parameters and quantify uncertainty in physical models of cloud and precipitation. This involves making comparison between observations such as advanced polarimetric and profiling radars and model simulations of weather. These efforts leverage the rich microphysical information content of observational systems to improve our understanding and model representation of cloud and precipitation processes. Furthermore, the Bayesian methodologies allow for robust estimation of uncertainty that can inform forecast representations of physical process uncertainty, e.g. via probabilistic forecast ensembles. Thank you so much.
Sorry, I should probably shorten that for next time. Okay, so yeah, I want to talk a little bit about this issue of constraining sort of basically how clouds are represented inside of climate models, and kind of from two different directions, what we call sort of top-down approach, where we're looking at satellite observations and what they can tell us about the climate, and then also sort of bottom up from more of a detailed process point of view. So, and then the other thing is that a lot of this work is, well, pretty much all of this work is collaborative and relying heavily on the work that Kate Loftus has done. Hopefully you guys have seen one of her talks. I don't know, I think she gave a talk earlier. And also collaborators, Greg Alcesser, Hugh Morrison, and so on. Okay. All right, so first of all, I did manage to sneak in some, I was just at the International Conference on Clouds and Precipitation in Jeju Island, Korea. So I figured I'd put in some weather here. So this is time lapse of a squall line hitting. That was a lot of fun. You can see some rotation in this cloud, by the way, right about there, which is kind of fun also. So of course, sometimes squall lines spawn up tornadoes and whatnot. So, and this is when it hit, and yeah, it was pretty impressive. Pretty strong winds, so pretty high precipitation. And I also mentioned that Kate Loftus sampled the storm in situ on her way to the conference. A little bit unfortunate, but, you know, the things we do for science. In any case, yeah, let me move on from there. Okay, so what's the big problem that we're dealing with? Well, the big problem is that we want to try to represent a lot of things that happen in the atmosphere, such as this cloud right over here. But what's the problem? Well, the problem is that our climate model grid scales are really big, right? In the climate model, we kind of break up the Earth into all these little grid points, and then we predict cloud properties on those grid points, right? Each grid point has, you know, maybe one or two numbers to describe the cloud population, and one or two numbers to describe rain, and so on. So it's really boiling down a lot. There's a lot that's happening here that gets boiled down into just a few numbers. Even if we go down to like weather models or higher resolution models, what they call storm resolving models or convection permitting models, the model grid is typically still missing a lot of these like sort of smaller little eddy features and smaller details of the updraft, and certainly is not going to resolve something like turbulence in the air. Okay, now once we actually, let's say we could represent those things. Even then you have an issue because you have basically like a population of droplets in the cloud, right? So there's a population of droplets of different size, and well, how do you characterize it? You can't follow every single drop. This is something that Kate brought up in one of her talks, that if you kind of grabbed a handful of cloud, you'd have around a billion cloud particles in your hand. So okay, you can't fall around a billion particles individually. So what do? Well, we just kind of stick a probability distribution on the drop sizes, right? And there's different ways that you can represent that probability distribution. So you just kind of like stick a function on it, right? Imagine that you stick like a Gaussian function on it that represents the distribution of drop sizes. You're more likely to find this size particle than this size particle, and so on. Or you could kind of chop it up into little chunks, right? Like a little histogram. And that's better in a way because, you know, maybe you have two peaks instead of one peak. There's newer, fancier methods where you actually do kind of follow around particles that are floating around in the cloud. They're called Lagrangian methods. And then each little super particle that you're following around actually represents many particles. So it's sort of like the particle congressman who is going to represent that population of particles in particle senate. I just came up with that, so please don't be too harsh in your criticism. Not a bad one, though, actually. Okay, anyway, going on. All right, let's say you could get every single particle, you still have problems. So if you look at just like two raindrops colliding, what happens to them? We kind of don't know. We kind of know, we kind of don't know. So this process of two droplets colliding is really nonlinear, and when they sort of break apart, this you see that there's a little filament over here. I should use a mouse for online people. There's a little filament here, and that's going to just like snap. And when that snaps, it could break up into just two nice little particles, or it could break up into dozens of tiny little particles. So it's a very complicated problem. That's just one process, right? That's raindrop collisional breakup. Okay, we go to ice, it gets even nastier. So, you know, you've probably seen snowflakes. No two snowflakes are alike. It's not really true, but in any case, they are messy, and like some of them are really weird shapes. And like if you look at the textbooks, they just show columns, just like hexagonal columns for these ice crystals. But they're not really exactly that. They have like weird features where they scroll inward. They're hollow. Sometimes they're not hollow. It's extremely messy. This is actually work that Joseph Coe and Kara Lamb are working on right now. I didn't tell you more about that. All right, and then there's like all sorts of processes like this. So like there's like up and down a cloud. There's every single process has, maybe not every single process, but almost every single process has uncertainties at that sort of process scale. So there's sort of a problem that's been called the double parametrization problem. We can't resolve clouds themselves in climate models, right? And then we can't resolve the actual processes that are happening inside the clouds. So there's sort of two scales of the problem here. So what does it mean? It means we have lots of uncertainty. Okay. Oh, and this is kind of an important thing, especially for this LEAP crowd, is that this means that there's no reference model for what happens inside of clouds, for cloud microphysics. And that's important because like a lot of machine learning methods really rely on having that reference model, right? You have a reference model, you generate just like absolute buckets of data, and then you train some other model on that reference model. And then you come up with some machine learning model that emulates your reference model. Great. We don't have a reference model here, so we can't necessarily rely on those techniques. Although they do have maybe limited relevance. Yeah. Okay, so looking at a climate model, this is, I'm going to be talking about the NASA GISS ModelE3 climate model. It's one of many climate models out there. We sort of polled the people who work on this model and asked for which parameters are most uncertain. We got this big old list of 45 parameters. It's quite a few. Some having to do with convective clouds, like that thunderstorm picture that I showed you before. Some having to do with what's called large-scale clouds. That might be something like these big marine fog decks that sit over off the coast of California. If you've ever been to California in the summer and expected a sunny beach day and been severely disappointed, you can think these large-scale stratiform clouds. And then there's the turbulence parameter here. Anyways, it's a lot of parameters, 45 parameters. And okay, well, if we talk to a statistician, they'll say use Bayes' theorem. You estimate the probability of some parameters given some observations. So parameters are X, observations are Y. And you know, it's just some way of combining some observational information and some prior information, basically. We just need to solve this and we get the probability of our parameters. It's too easy, really. One thing to mention here is that we have this condition, it's conditional on basically any other assumptions in our model. So we make lots of assumptions in our model, right? Way back here when we simplified our model into these things, that's an assumption. Right? That's something that's baked in. So whatever we do, we can estimate the uncertainty in our parameters, but it's always going to be sort of conditional on all those things that we've baked into our model. Okay, what can we use to observe? We have a bunch of satellite metrics. There's things related to radiation, water vapor, specific humidity, temperature, and so on from various satellite sources. So some of these might be a single satellite, some of them might be multiple satellites. Sometimes there's a single multi-satellite product. Sometimes there's multiple products from different satellites. Interestingly, I think it's interesting at least, sometimes these disagree. Sometimes they disagree by an amount that's actually greater than the published uncertainties of each observation. So that's a little bit scary too. But in any case, there is observations. They have some uncertainty. Luckily, that Bayesian sort of framework that I showed allows us to incorporate uncertainties. Okay, how do we do this? Well, if our model was linear, this would be easy. So let's say our model is linear. We vary our parameter in our model, right? Any one of those 45 parameters. And we look at some measurement, and it has a nice linear relationship. Beautiful. We have some observation. That observation has some uncertainty. And it's basically just projecting this uncertainty onto the model down to the parameters. And then we get our uncertainty in our parameters. And wow, look, this is Gaussian over here, a nice Gaussian function, and we get a Gaussian back. This is very easy. It's very nice. Unfortunately, our models are nonlinear. They don't have these simple behaviors. And nonlinear models are harder. So if our model is nonlinear, it has some nonlinear variation of the outputs of these measurable quantities with variations in the parameter. You don't get a simple Gaussian. You get something that's really kind of lumpy. And well, there's a bunch of simple methods that you can use here for parameter estimation that are really easy, really powerful, they work really well, that completely fail over here. So what the bottom line is, you have to use Markov chain Monte Carlo or similar techniques if you want to get at this quantifying these uncertainties and estimating parameters. Now, what is that? All right, so basically what this is it's an iterative method where you sample a point in your parameter space. So you say, I'm just going to guess that I have these parameters. And then I take a step away in that parameter space. I just like move. And then I look and see if my model performs better with those new parameters or worse. And then depending on whether it's better or worse, you accept or reject. And you kind of just keep on stepping around in this way, building up a whole chain of points. And if you look at the end of what points you've selected, they kind of, they're basically samples of the underlying probability that you're trying to estimate. So that's kind of nice. You just have to run it more times. In this case, yeah, times. Okay, that's great, wonderful. So I'm just simplifying that methodology into this cartoon. Sample our parameters, run our model, we compare the observations, and then we iterate again. But the problem is that climate models are expensive, right? So, oh, by the way, if anyone, if you want me to stop at any point or ask a question or anything like that, I'm happy to pause. If I miss something or don't describe anything well, please just interrupt me. Okay, this is too expensive. Climate models are expensive. We can't do this a million times. We can't even do it, 100,000 or 10,000 times, or 1,000. We're getting maybe a little bit closer to the realm of plausibility. But then, like, these methods don't really work well if you just have 1,000 samples. So what do we do? Well, okay, I'm at Leap, so of course we use machine learning. So what we do instead is we sample our parameters in a relatively limited way. So we maybe do 500 samples of our parameters, sort of across the range of uncertain values. We run our model, and then we train a model surrogate. Sometimes we call this an emulator, although people use the word emulator or surrogate for different things. Anyways, we train a model surrogate, and all this model surrogate does is basically relate variations in the parameters to variations in the parameters to variations in the output. It doesn't do anything else. You ask it for specific outputs. It doesn't simulate all of the processes inside of the climate model. All it says is if I played around with this parameter, what happens to all of the outputs? Okay, and that's all we need for this, because we stick it into this framework where we basically replace it for the purposes of parameter estimation. And yeah, again, let me emphasize that we only replace it for the purposes of parameter estimation. We don't take this emulator and then try to simulate the climate. It's very simple. It only knows this very limited sort of sensitivity. But then we have parameters which we can run in the full model. That's how it is. Okay. So what do we get? We get this beautiful diagram, this beautiful 45-dimensional probability distribution that's completely uninterpretable and not very helpful. But in any case, the few things that we want to pull out of this is that basically we started out with flat distributions for each of these parameters. And then we've gained information, right? So this one, if I could zoom in, way up here in the top left, it now has like a little peak. So it's constrained the parameter down to a plausible range, right? By comparing the model to observations. And similarly, basically, almost all of these parameters have been constrained to some extent by our observations. That's great. And we have uncertainty too. It's not just a single value, right? It's a probability distribution telling us what the likely values are. And if we plug this into our climate model again, we can look at how well we did. So we can look at certain outputs. This is long wave cloud radiative effect and precipitation. And these lines are sort of our target. And this sort of is maybe our tolerance or our uncertainty in the actual observation of precipitation. And these black points are what we started out with. And these green points are sort of the final of what we've got. And so that's sort of zeroed in on these points. So, okay, that's good. And just to sort of drive this point home, in our original sampling, so we ran 450 parameter values through the model. Basically, 0 of those produced a realistic climate. And our final sample, out of 100 samples drawn from that, 30 of them were good. So we've gone from basically a 0% success rate to a 30% success rate, which is a huge improvement for us. And the sort of important thing here is that like those 30 samples are very different parameter values, and they produce like different model behaviors, but they all basically agree with observations. So this is sort of something that is kind of interesting from the point of view of climate modeling. In climate modeling, you have these model intercomparison projects where you take different models from different centers and you compare them together. And people look at that and they say, okay, well, do the models agree? They usually don't. And when they don't agree, that uncertainty is sort of viewed as some sort of informative uncertainty of how well we understand the climate. But really, these models have just been created with different methodologies. So they're not necessarily, that uncertainty is not consistent. It's been produced by sort of just the opportunity of many groups putting together different climate models in different ways. This sample of parameters is sort of all parameters that have been constrained in the same way, some sort of consistent way. So we think of this as, we call this a calibrated physics ensemble. And it's basically a way, maybe one of the first sort of fully realized attempts at characterizing the uncertainty in the climate model. And it would be nice to compare these results to similar results from different climate models. Yeah, I'll skip that bottom line for now. As I said, so if we compare just like sticking in the regular values into our climate model, we get a big spread in this shortwave, observed shortwave. And like these values out here are bonkers. They don't make any sense. So if you just perturb the parameters and you look at what your model's producing, it produces lots of crazy values. So it doesn't necessarily make sense to analyze your model on those values. What we get instead with our calibrated physics ensemble is they're all in reasonable agreement with observations, more realistic. Okay, I think I'm going to skip this slide and go to this one. sometimes people like to perturb parameters in models and then say, okay, which ones are the important ones to perturb? And then kind of throw out the ones that are not important. So you might get like, you know, this is just a correlation. You might get, and these are all parameters, and these are all outputs, and basically where you have reds or blues, you have stronger correlation between the parameters and the outputs. So you might say, okay, well, maybe these ones I can throw out, but these ones look really important. This one looks really important. Okay, you might like pick and choose and throw some out. People do this quite often. But if you start to look at other metrics, so here, this is a sort of metric that shows how much the uncertainty varies in an output as you perturb a parameter. You see other parameters are important for that. Okay, so that's interesting, right? Moving on from there, if we compare our initial perturbed parameter ensemble, that's just sampling across the parameter ranges, versus the constrained one, the one that's been constrained by observations, then we also see a completely different picture. So here, like, there's a zillion parameters that are important. It's hard to pick out a parameter that isn't important, sort of after constrained by observations. So there's a big difference between looking at the sensitivity of a climate model by perturbing parameters when you're just perturbing the parameters and when you're perturbing the parameters in a realistic way, a way where you actually are producing a simulation that has any matchup to reality whatsoever. So that's sort of an important point. Somewhat, yeah.
With a question about that, like, what's different between when it becomes more sensitive or not? Is it like just the ranges of what you call a perturbation, or is it like the parameters themselves?
Yeah, I think that's mostly it, is that we've basically constrained down the range of perturbations down to more realistic range that produces realistic results. It's a little bit more complicated than that because there are sort of covariances in the parameters, but basically we've just reduced it down to what produces acceptably realistic simulations. Okay, we can also do other fun stuff with this sort of calibrated physics ensemble approach. One thing we've done is we've like asked ourselves, like, well, what if I have better observations in the future? So I can look at all of my parameter values, all of my parameter PDFs, and I can compare what I get as constraint on the parameters with sort of default uncertainty in some observable quantity, versus if I had a better observation of that quantity, one with less uncertainty. So in other words, how much is each observation giving me? If I sent out a new satellite to outer space, how much information would I gain on my parameters from that new observation? So basically, I just have the PDFs comparing like the default uncertainty with a new lower uncertainty, and you can kind of look at which processes, which parameters related to which processes get sort of constrained. So if you're developing a satellite, we can now give information about like, how valuable will that actually be for physics. Okay, so stepping back a little bit again, for some of these things, we get a good matchup. This is basically outputs from the model. These green crosshairs are sort of those observational targets from the satellites. The black dots are our original ensemble, and the green dots are sort of our final. Great, we get a good matchup. Pretty good. For some of these, we don't, though. Okay, so this is a total cloud cover, and this is a shortwave cloud radiative effect and liquid water path. So basically, we're able to match the total liquid water path, total amount of liquid that's in clouds, and the cloud radiative effect, but only if we have too few clouds. So in other words, our model is basically getting the right radiation by making too few clouds that are too shiny. That's basically the answer. And this is actually like something that's pretty common in climate models, that they tend to make too few clouds that are too shiny. And we kind of show here by looking at this, these perturbations in our parameters, that this isn't because we don't have the right parameter values, right? No parameter values can get us at the target, right? This is something that's likely structural. probably associated with a lot of those assumptions that we baked in. If you remember when I had the Bayes theorem there and I said it was conditional on those assumptions, this is basically an effect of that, right? We're not able to get at our target because of some structural things in the model. So what structural changes need to be made? Okay. Let me just say that we would like to guide a lot of this with detailed observations. So this is maybe taking another step back. But we don't just want to look at climate models, we can also look at detailed cloud models. Right? So this is an image from a large eddy simulation where you just resolve a lot more of the clouds. It's very high resolution. Solve part of the sort of turbulent cascade phenomenon. So we would like to sort of inform all of our decision makings with structure, with parameters, both in this sort of detailed way from bottom up, but also with the top down from the satellite observations. So we'd like to be able to meet in the middle in some sort of intelligent way, some sort of way where they can talk to each other. And well, what's one way we can do that? We have observations, for example. This is satellite I'm sorry, this is not satellite observations. These are ground-based radar observations of clouds. This is basically columns. I should have cited this paper. This is from Silver et al. Sorry about that. I think it's 2022. These are sort of samples drawn from something like this large eddy simulation. So we can sort of make this comparison there. And then we have what's called a single column model, which is a representation of our global climate model, but just a single column, just like take out a single column and we simulate just one column of that. And the nice thing is you can basically set up the situation to simulate this large eddy simulation, the single column model in the exact same way. So this might be some way to sort of make that translation across skills. We could do a consistent comparison between these two and then perhaps a statistical comparison with the observations. That's sort of the hope. And we've played around with this a little bit. We basically ran those same parameters that I showed you that we run with the global model through a single column model for some specific cases. So we have a single column model case that predicts trade wind cumulus, the sort of cumulus that might look pretty on vacation in Barbados, I guess. And we can look at the range of values that we produce, that's in black, with our perturbed parameter ensemble, and then the values that come out of our constrained, our calibrated physics ensemble. That's like after constrained by satellite observations. So you see a pretty big difference in behavior there, and we can also compare it to what large eddy simulations do. And so I plugged that into the framework for a few cases and got out a posterior distribution. And obviously, we don't have a lot of constraint here, but this actually is encouraging in that what we've done is basically reduce the parameter volume by about 40 times. So we've made estimating the parameters about 40 times simpler than it was before. If you have less space to search in, then it makes it more efficient. So that's just one step in that direction. Not there yet. Okay, going back to this, I don't know why I put this here again. Oh yeah, we want to address the processes. So we have basically, do you have a question? Yeah.
Can you briefly re-explain how you constrain the parameter space? Like how you made it 40 times smaller?
Yeah, so I basically did the exact same framework that I did for the global model, but for each parameter selection, I ran 3 single column model cases. And the single column, one was a drizzling stratocumulus, one was a trade cumulus, one was a precipitating trade cumulus, and I compared it to sort of an ensemble of large eddy simulations, so the detailed high resolution models, what they produce. And I said, okay, the single column models should match this within some tolerance. And then I did the Bayesian parameter constraint to constrain down these parameters. So basically, I view this as like a methodology, as like a first cut before you apply the satellite observations. And running the climate model is super expensive. Single column models are cheap. So I can do this very cheaply, cut down on the samples that I run through my full climate model and make the whole process hopefully a lot more efficient and a lot more, basically won't waste as much time looking at bad parameters, if that makes sense. And yeah, this whole idea isn't that new. There's this paper from 2003 where there's this sort of chain in between these things, where our global models are being informed by single column models. I think my battery's dying. And also by observations and these high resolution models. Okay. So getting down to the process level, well, we've made all these assumptions in our climate models. How do we get around that? How do we deal with that structural element? We've come up with basically a structurally flexible microphysics scheme where we do certain things that haven't been done in the past. So if you remember when we had those little distributions, for the size distribution of cloud droplets, we don't assume any functional form for that. We predict moments of the size distribution. So these are quantities like number or mass or other quantities. We include whatever limited physical constraints do exist, but we don't add ones that do not need to be added in, that we don't know for sure. And then we can choose whatever quantities we want, basically, to describe the cloud. And we can use Bayesian estimation to figure out all of the parameters of that, basically. So this is something that Kate is working on right now, basically trying to get our Bayesian microphysics scheme, which we call BOSS, to match up with a more detailed model, which, you know, I did say there's no reference, but there are models which are more complicated. So one question is, can we reproduce those complicated models with our less complicated model? And I won't go too much into what she's done. She's basically run this a billion times with different parameters and then used this sort of reference model as a constraint. So this is sort of without constraint, and this is with constraint. So yes, I won't go too much into that because that's her work. But we have a question. So sorry, I should skip past this. Just get to, how well does it actually work? We actually stick this into a climate model. Does this work? So we actually tried this. This is with a collaborator, Kulun Ma, at PNNL in Washington. And if we look at sort of observations, this is global observations of shortwave and precipitation, and the default version of the DOE's climate model over here, you can see sort of values here, average -45, average -60, and BOSS gets a lot closer to that. Okay, that's good. Precip is basically unchanged. So that's sort of a encouraging result. But I will say that I think this is mostly by accident. Like we didn't actually tune BOSS in the climate model. We tuned it in those detailed high resolution models and then just stuck it in here and then hoped it worked. And it did work. But I don't think that's necessarily the most robust result. It requires a lot more testing. The main thing here is that it didn't cause the model to blow up, and it's a promising avenue for further work. Okay, I want to just go back actually to this. So there are other structural issues in clouds and precipitation that can be readdressed. So traditionally what we've done in the past is break up droplets into cloud droplets and rain. But this is really artificial. Like, when does a cloud become rain? When does rain become a cloud? If it's evaporating? And it requires also all these processes. So I might ask the question of, when two cloud droplets bump together, do they make a larger cloud droplet or do they make rain? So that's basically the difference between self-collection and auto-conversion. Whoops. And then we also have to have a process of accretion, where basically rain bumps into cloud droplets, it makes bigger rain. So we have basically 4 processes that we have to simulate here, when in reality, there's only one process in nature, right? It's just droplets bumping into other droplets. So by moving to sort of a single category approach, you can actually get rid of a lot of this complexity. So Kara Lamb, who's here, I believe, also has a recent paper on this, on some work using machine learning to investigate this. And there's also recent work by Adele Eigel that looks into this. I won't get into the details of this plot. Basically, if you assume a single category, you get lower error than if you assume 2 categories. Okay, and then this has been taken up by Adele's former PhD student, Arthur Hu, who's now doing a postdoc here at Columbia. And this is, yeah, similar work. may perform better with the unified cloud rate category. That's sort of the bottom line there. And the reasons are a little bit complicated, but he has lots of nice explanations here why. I won't get into the details, but if you have questions about that, I'm happy to talk about it. Okay, we went through that. All right, and then putting it all together. We want to be able to sort of unify this sort of these two things we're doing. This work on the full climate model, both the global version and the single column versions. And this sort of bottom-up work where we're figuring out how to best represent clouds, testing out things like BOSS as an approach for doing cloud microphysics. And we want to join them together. So this is sort of the very first step at doing that. Basically what Kate did is she ran BOSS with different parameters many times for the single column model. And so this is a time series of liquid water path. That's just the total amount of liquid you have there, and rain rate. And then compared it to what the high resolution models say we should get. Those are these sort of black lines. And then also played around with evaporation a little bit. Just did some tweaks to that she thought made sense in the structure of how evaporation is calculated. So this is just sort of first attempt, but basically our goal would be to use constraints like this. So which of these many lines that are from parameter variations in BOSS in Model E match up with these observations. So that's sort of the next steps. All right, so hold on a second, not so fast. Why? You say not so fast. Okay, there are issues. So one of the issues is that basically if you have a grid and you have processes that are happening inside of that grid, but you assume that there's some variability inside of that grid. Okay, so what do I mean? Well, if I take a cloud and I look at a cloud, it's not going to be across a climate scale grid box doing the same thing across that whole, say, 100 kilometers, right? Clouds are, if you look at clouds, they vary along pretty small scales. So actually, most of our models have this built in. We assume that there's some variability in the cloud properties across that grid. Okay. And the reason we need to do that is that when you have a process that depends on those quantities, those cloud quantities, and that process is nonlinear, you can't just average it out. In other words, taking the mean properties of those clouds and calculating your process rates won't actually give you the right answer. So it's just you can't average out something that varies nonlinearly. So when we sort of turn that on, sometimes with BOSS and climate models, we get crashes. So that's one thing. And it might be just because of the parameter values we've chosen. Another thing, and maybe a more scary thing, is that, well, in climate models, you solve on time steps. So you say, what's happened in the last 5 seconds? I'm just joking. What happens in the last 10 minutes or 30 minutes? Okay, usually they're pretty long time steps. So a lot can happen in that amount of time, right? And a lot can vary in a nonlinear way in that amount of time. Right? And this is kind of a problem because if you look at the behavior of a climate model, trying to solve the physics at different time steps, I'm going to solve it at 15 minutes, 10 minutes, 5 minutes, the values don't converge. So you don't get convergence. You're not reaching some point where you're like, this time step is good enough. Right? We get different values in the behavior of our model as we're increasing the time step. So this is a tricky thing to deal with. And basically what it means is that you can learn the physics as best as you can in your high resolution models, and you're still going to have difficulty running it in climate models that aren't solving it at the time steps that it needs to be solved at. So these are sort of existing challenges, and yeah, they're being worked on. But there are issues with basically trying to solve these things. Okay, so just sort of summing up. What have we done? Well, we've done a few different things, sort of a spectrum of ways to constrain microphysics and other processes inside of climate models. We've done sort of directly fitting process rates to some reference scheme. I didn't really talk about this work. We've also started fitting things in high resolution models. That's Kate Loftus's work. And we've done this in climate models also with satellite constraints. So sort of these things have been sort of checked off. And we have yet to do sort of constraint of our physics with weather scale data. So actually observing a cloud right now as it's evolving over 10, 30 minutes, using that to inform our physics. This is really important because if you look at, if any of you are like weather nerds, you can look at like the American network of precipitation radars, and it's spectacular. You have like hundreds of radars across America measuring precipitation, measuring storms every single day in 3D with multiple variables. It's incredible. It's really fantastic. How much of that data goes into learning what the physics of precipitation is actually doing? 0%. I'm rounding off here, but basically 0%. We're throwing out all this data. So we basically haven't figured out a way to use that data. Certainly not in a systematic way. So anyway, I'll get off my soapbox now. Okay, takeaways to do. We've done this parameter estimation inference. We've sort of done it in top-down and bottom-up. I would say the top-down is pretty good, and the bottom-up seems very promising. But yeah, the meeting at the middle is going to be tricky. Okay, calibrated physics ensembles. This is like one of our big pushes that we're trying to push for, is basically don't just vary your parameters and expect it to mean something. We really want to look at which parameter variations are actually matching up to about what the planet is actually. So right, we can constrain our microphysics in high resolution simulations, large eddy simulations, doing bottom up. And then there's these challenges that exist. Subgrid variability, numerical errors. These are sort of things that we still need to tackle. And then there's this separate issue of structural errors in the bottom-up method, right? Even if you have a high-resolution model, well, am I representing cloud and rain as two different categories? That introduces error. So there's still this issue that's being addressed. Recent work by Carol Lamb, Adele Eigel, Arthur, Andrew Gettleman, and ongoing work by Kate Loftus and Sean Santos, if you're interested in digging up their names. And that's it. I'm happy to take any questions. And yeah, I guess we have food also.
Do you think the scale application is going to be easier for CESM? Sorry. Do you think the weather scale applications would be like easier than a global ECM because of the like subgrid variability and sub time step variability, or are there like specific challenges that you see with that?
It's a good point that you wouldn't have to worry as much about that, but no, I think it's going to be a lot harder. And the reason why is basically because, if you look at what like weather forecasting centers do, they do data assimilation, where they are basically run an ensemble of models that don't have different physics, they have different initial conditions. And that's because if you vary the initial conditions in your simulation, you get pretty different behaviors of what weather you're forecasting. And we can also not really measure the state of the atmosphere that well, right? If you think about what are we measuring in terms of the atmosphere, we send out balloons like twice a day that get profiles of the temperature, humidity, and winds, and that's super important for models, right? I would say it's more important than like satellites and stuff like that. Nobody will talk about it, but some other people will talk about it. But basically, that's a huge uncertainty, is that state uncertainty. So if you have a misfit in your model and your observations, is it because your state is uncertain, right? Your initial conditions that you put into the model are uncertain, or is it because your physics is bad? Really, it's both, right? But how do you disentangle the two? So that problem of simultaneous state and parameter estimation is one of the really big ones. And it's also why Pierre was starting to look into data simulation. Right? It's because that is a really big problem with huge potential benefits. You can leverage all this information. Yeah, that's a fantastic question. What is the final model? Softball question. Actually, that's really hard. Everyone wants lunch.
What, could you just reiterate what you think the structural errors are? Why you, like, you know, converging on, like, good parameters didn't help?
Yeah, there's some issues in, so this is something that this is like Kate's big bugbear, is all of the sort of crimes of how clouds are represented in climate models. So one of the things is that they don't take into account in the right way, basically how the cloud size distribution changes in width. In other words, they assume that the cloud distribution tends to be a lot wider than it is in nature. There's a recent paper actually by somebody who like flew some instruments through clouds and found really narrow distributions. And those are going to behave in a very different way than like very broad distributions. That variability isn't really captured in models. So that's one of them. There's others.
Marcus, could you a little explain about that single column model? How we can find a relationship between a single column model and the model that try to do in a distributed way?
Yeah, so the single column model is you kind of pluck a column out and then you give it forcings that are sort of matching some forcings that are representative of some weather phenomenon that you might have studied in more depth. So very often they come out of field campaigns. Right? There's an extensive field campaign that looks at what the large scale flow is in an area, what the temperature and humidity profiles are with just like way more observations than you normally do. So you can really constrain what's going on. And then you can hopefully derive that single column in a way that's consistent with what you've observed and produce an atmosphere that behaves consistently with what you've observed, if you got the physics right. And you can also put those same forcings into a high resolution model that has periodic boundary conditions, for example, and then compare that behavior to the single column models from the climate model. But basically, the single column model has all the same physics as the global climate model. It's just instead of having, you know, advection, things coming over from the next grids, it just has some assumed forcing changing.
And do you think if we emulate a single column model with the ML model, can we use that ML model to substitute for a distributed model? Because this is one of our problem in the aerosol.
Yeah, that's a good question. I think it'd be complicated. And I think also, you know, you'd have to tie that to the numerics of advection in the global model. So you still have to, if you had just an ML model saying how that single column model responds to forcing, I think you'd still have to figure out how it's connecting to its neighbors. Yeah, I don't have fully formed thoughts on that, but that's interesting. Thank you.
Hey, can I pipe up? I got a question.
Hey, hold on, Robert has a question.
Yes. Thanks, Marcus. That was entertaining as always. You started at the beginning and you said there's no reference model. And then you used a bunch of reference models instead of using observations directly, right? I mean, that is to say,
Robert, can you hear us? Robert, you're cutting in and out. If you put your question into the chat, we can just read it for you.
Okay, hang on. Let me see that.
Yeah, so Robert highlighted a important element of hypocrisy in my talk, because I said that there are no reference models, and then I used exactly those reference models as a reference for our microphysics development. This is very true. So yeah, we basically trained our bulk model, so going back to difference between bulk and bin. We trained our bulk model, right, this thing, on a bin model, which is this thing over here. And yeah, it's because that's all we have. And getting to observations is another step that is very hard at those sort of scales, at the scale of actually resolving what's happening inside of clouds. So that's just why it's a stepping stone to just say, this is more complicated than my bulk scheme. Can I fit it? Data simulation uses observations, at least indirectly. Yes, that's true. It would be nice to do data simulation. It would be nice to do joint state and parameter estimation. I don't know anyone who's done that successfully for like a large number of parameters. An observation somehow more indirectly informative about microphysics. Maybe, yeah. Maybe there's a way to look at that in a way that you don't worry about the state error. Okay, hopefully that answers your questions, Robert. Okay, thank you.
Thank you, Marcus. And everybody, please help yourselves to lunch in the kitchen behind you and stay in chat for a while.